Equality of matrices. As we dive into the study of matrices, you will find that it is often necessary to determine whether two different matrices are essentially the same. In mathematics, this specific concept is formally known as the equality of matrices. Now, it is important to understand that for two matrices to be considered equal, they cannot simply be similar. They must be identical in every possible way. This means they must be perfectly matched in both their structure, which we will define as the order of the matrix in the upcoming slides, and in the actual numerical values they contain. Hello everyone! Today, we are beginning our lesson on a fundamental concept in linear algebra. Understanding the concept. Now that we have a general idea of what it means for two matrices to be the same, let's look at the formal requirements. For two matrices, matrix A, represented by elements A sub ij, and matrix B, represented by elements B sub ij, to be considered equal, which we write simply as A equals B, they must satisfy two mandatory conditions. It is important to note that these conditions are non-negotiable. If even one of these two requirements is not met, the matrices are automatically not equal, regardless of any other similarities they might share. In the next few slides, we will break down exactly what these two conditions are. Condition 1, same order. Now, let's dive into the first mandatory condition I mentioned in the previous slide. The matrices must have the same dimensions. To put this simply, it means that the number of rows in matrix A must be exactly equal to the number of rows in matrix B. And similarly, the number of columns in matrix A must be exactly equal to the number of columns in matrix B. In mathematical terms, if matrix A is of order m by n, then matrix B must also be of order m by n. If these dimensions do not match perfectly, the matrices cannot be equal. To illustrate this, imagine you are comparing a 2 by 3 matrix with a 3 by 2 matrix. Even if they contain the exact same set of numbers, they are automatically unequal because their structures are different. Once we have verified that the dimensions are identical, we can then proceed to the second condition, which we will explore in the next slide. Condition 2, identical corresponding elements. Now, once we have confirmed that the orders of the two matrices are identical, we move on to the second mandatory requirement, examining the individual elements. For two matrices to be considered truly equal, it is not enough for them to just be the same size. Every single element in matrix A must be exactly equal to the element occupying the same position in matrix B. In mathematical terms, we express this condition by stating that element A sub ij equals element B sub ij for all possible values of I and j. To put this into perspective, the element located in the first row and first column of matrix A, which we denote as a 1, 1, must be exactly equal to the element in the first row and first column of matrix B, denoted as B 1, 1. This same rule of correspondence must hold true for every other position across both matrices. Real-world analogy, the digital spreadsheet. Now that we have discussed the two mandatory conditions for matrix equality, let us put these theoretical concepts into a real-world perspective to make them easier to visualize. Imagine two students, Rahul and Priya, who are both creating a digital spreadsheet to track the marks of 3 different students in 2 specific subjects, mathematics and science. First, let us consider the order of these spreadsheets. For Rahul's and Priya's files to be considered equal, they must have the exact same structure, meaning both must have exactly 3 rows for the students and 2 columns for the subjects. If Rahul were to add an extra column to include marks for English, the spreadsheets would no longer be equal in structure, regardless of the numbers inside. Next, let us look at the elements. Even if the structure is identical, the spreadsheets are only truly equal if the data within every single cell is exactly the same. For instance, the mark for student 1 in mathematics must be identical in both files, the mark for student 1 in science must match, and so on, for every single cell in the table. By thinking of matrices as spreadsheets, you can see why both the dimensions and the individual values must be perfectly aligned. Now that we have this conceptual analogy, let us move forward to some step-by-step mathematical examples to see how to apply these rules in your exercises. Step-by-step examples. Now that we have established the theoretical conditions and looked at the spreadsheet analogy, let us apply those concepts to a practical example. Please look at example 1, where our goal is to determine if matrix A and matrix B are equal. Matrix A is a matrix with the first row containing 2 and 5, and the second row containing -1 and 0. Matrix B is presented with the same values in the same positions. To solve this, we must strictly follow the two conditions we discussed in the previous slides. First, we move to step 1, checking the order. We can see that matrix A has 2 rows and 2 columns, which means it is a 2x2 matrix. Similarly, matrix B also has 2 rows and 2 columns, making it a 2x2 matrix as well. Since the dimensions are identical, the first condition for equality is satisfied. Next, we proceed to step 2, comparing the corresponding elements. We must ensure that every single element in matrix matches the element in the exact same position in matrix B. Starting with the first row and first column, both matrices have the value 2. Moving to the first row and second column, both have the value 5. In the second row and first column, both contain -1. Finally, in the second row and second column, both contain 0. As we can see, every corresponding pair is identical. Therefore, our conclusion is that, since both the order and all corresponding elements are exactly the same, matrix A is equal to matrix B. Now that we have mastered simple verification, in the next slide, we will explore how to use this logic to solve for unknown variables, which is a very common application in your grade 12 curriculum. Step-by-step examples continued. Now that we have seen how to verify if two matrices are equal, let us move on to a more practical application. In example 2, we will focus on solving for unknown variables. This is, in fact, the most common way you will encounter the concept of matrix equality in your grade 12 mathematics curriculum. Let us look at the problem. We are asked to find the values of x and y. Given that a 2x2 matrix containing x plus 3 and 4 in the first row and 2y and 7 in the second row is equal to another 2x2 matrix containing 5 and 4 in the first row and 10 and 7 in the second row. To solve this, we follow a systematic 3-step process. Step 1 is to identify the equality. Because the problem explicitly states that these two matrices are equal, we can apply the rule we discussed in the previous slides. Their corresponding elements must be identical. Step 2 is where we equate these corresponding elements to form simple algebraic equations. First, looking at the first row and first column, we can see that x plus 3 must equal 5. Next, looking at the second row and first column, we see that 2y must equal 10. You will notice that the other elements, 4 and 7, are already identical in both matrices, so they simply confirm that the equality is possible. Finally, in step 3, we solve these equations for our unknown variables. For x, we subtract 3 from both sides of the equation, which gives us x equals 5 minus 3, resulting in x equals 2. For y, we divide both sides by 2, which gives us y equals 10 divided by 2, resulting in y equals 5. Therefore, our final answer is that x equals 2 and y equals 5. While this process seems straightforward, there are a few pitfalls you should be aware of, which we will discuss in the next slide regarding common mistakes to avoid. Common mistakes to avoid. First, avoid ignoring the order of the matrices. A frequent mistake students make is jumping straight into comparing the individual numbers without checking the dimensions first. Always verify that the orders are identical. For instance, if one matrix is a 2x3 matrix and the other is a 3x2 matrix, they are automatically unequal, regardless of whether they contain the same set of numbers. Second, be careful not to misalign the elements. When comparing two matrices, you must be precise about the position of each value. Do not compare an element from the first row of matrix A with an element from the second row of matrix B. You must strictly follow the rule that the element at row I, column J of matrix A must be equal to the element at row I, column J of matrix B. Finally, be vigilant regarding sign errors. As we saw in the previous example where we solved for the variables x and y, the equality of matrices often leads to simple algebraic equations. A small slip in signs can lead to an incorrect final answer. For example, if you encounter the equation x minus 3 equals 5, remember that x equals 8, not 2. Now that we have walked through the theoretical conditions and some practical examples, let us discuss some common pitfalls. It is very important to be mindful of these mistakes to ensure your answers are accurate. By keeping these 3 points in mind, you will avoid the most common errors associated with this topic. Key takeaways. First, always remember the 2 mandatory conditions we covered earlier. For matrix A to be equal to matrix B, it is not enough for them to just look similar. They must have the exact same order, and every single corresponding element must be identical. If either of these is missing, the matrices are not equal. In terms of mathematical notation, we express this as a sub ij equals b sub ij for all values of I and j. This is simply the formal way of stating that the element in any given row and column of the first matrix must be exactly the same as the element in that same row and column of the second matrix. Finally, let's consider the practical application. As we saw in our second example, the concept of equality is a powerful tool. It allows us to create a system of linear equations by equating corresponding elements, which then enables us to solve for unknown variables hidden within a matrix. Now, let's wrap up everything we have discussed by reviewing the key takeaways on this final slide. Keep these points in mind, and you will have a solid foundation for solving any problem regarding the equality of matrices.